Thank you, Elizabeth. So I think now we're ready to start the panel discussion. We will introduce the speakers, but let me first introduce the moderator of today's discussion, which is Erik Curiel, who is now affiliated with the University of Bonn and with the Black Hole Institute in Harvard, and he's a philosopher of physics and has written quite a bit about information loss. And we're delighted to have him as the moderator of this panel discussion. And of course, we have three wonderful panel members, who Paolo will introduce.
Of course, I have the honor to do that, so I hope to be up with it. We have three, let's say, plenary speakers, I guess. Let's say we might start with Professor Carlo Rovelli, that you probably know very well, but let's say just to give a brief introduction about him, Professor Carlo Rovelli is one of the founders of Loop Quantum Gravity, you know probably, and he earned his PhD in 1986 at the University of Padua, and he currently leads the quantum gravity group of the Center of Physics Theoretic of the Marseille University. He is an adjunct professor at the Department of Philosophy of the University of Western Ontario. He is distinguished visiting researcher chair at Perimeter Institute. And he has been author or co-author of more than 200 scientific papers. He's author or co-authors of two books about loop quantum gravity, and he also well known for his works on foundation of quantum mechanics and also for his popular science books. And he received several awards. We can mention, for instance, the Xanthopoulos Award in 1995 for his contribution to theoretical physics. And then we have the pleasure to have Suvrat Raju, Professor Suvrat Raju, who is a leading expert in quantum gravity at the SCFT correspondence, holographic dualities, and let's say their connections to black hole information paradox and entanglement. He earned his PhD in 2008 from Harvard University, and since 2012 he has been professor at the International Center for Theoretical Science, which is part of the Tata Institute of Fundamental Research in Bangalore, probably you know. Among the awards, he received the ISTP Prize in 2019 for his contributions to the holographic description of black hole interiors, and the Nishina Asia Award in 2022 for his influential insights into the black hole information paradox and holograph. And finally, we have Professor Bernard Kay with us. Professor Bernard Kay is Emeritus Professor in the Department of Mathematics at the University of York in UK. He's a mathematical physicist working at an interface between quantum field theory, quantum gravity, and fundamental problems in quantum theory. He obtained his PhD in 1977 at King's College London under the supervision of Chris Shishan, and during his academic career he has held visiting research positions to several institutes, including in the Institute for Advanced Study in Princeton, the University of Rome, the Enrico Fermi Institute at the University of Chicago. He obtained the Leverhulme Research Fellowship in 2002, and his work is mainly focused on mathematically conceptual aspects of quantum field theory in core spacetimes, including black hole evaporation, scattering of classical and quantum waves on black holes, and quantum gravity issues. So I think that we have a great panel to discuss the information paradox problem, in my opinion. So we hope that you will enjoy the discussion and the panel with us.
Shall I take over? Okay. Before I start, I actually confess I have forgotten. Are the panel presentations supposed to be 15 or 20 minutes long?
15.
15. Thank you. Okay. So as moderator, it will be my great pleasure to viciously enforce the 15-minute presentation length, so that we have plenty of time left for Q&A. And as I like to say, I don't make the rules. I just enforce them with arbitrary viciousness and whimsical cruelty. So I'm going to take advantage of my status as moderator to make a quick remark and pose a quick challenge before the panelists dive in. So my remark is that it's really, I think it's important, especially for the audience, to keep in mind while listening to the presentation that although the information loss paradox is, well, as I just said, implicitly, is always granted the honorific of a definite article, as though there is one, the information loss paradox. There are actually at least 5 different articulated proposed versions that have been discussed in the literature. And that, when I say 5, I mean that's a very coarse graining. That doesn't even take account of the ambiguity in words like unitarity and things like that. So, you should keep in mind that what each of the panelists says, what their version of the information loss paradox may not be exactly the same as those of the others. And it's good to keep in mind how what each says about their own version does or does not apply or bear on what the others say. My challenge is I would love to have someone tell me, to convince me, that the information loss paradox really is important for quantum gravity, that it's an important problem to address for quantum gravity. Because the information loss paradox occurs in the context of an evaporating black hole in a space-time in which quantum effects are taken into account. So it's manifestly an object that we theoretically treat in the framework of semi-classical gravity. But semi-classical gravity is just, we all, I think, or at least most of us, almost all of us, think that semi-classical gravity is just an effective theory. And I mean that in the sense of high energy particle physics effective theories, where you integrate out degrees of freedom to ignore all the stuff that's irrelevant for the regime you're interested in, or in thermodynamics, condensed matter, where you construct effective theories by coupling your system to a coarse-grained environment. And in all these cases, you lose unitarity all the time. And no one ever worries about it because we know why the unitarity is being lost. We integrated out degrees of freedom. We've coupled the relevant degrees of freedom to a coarse-grained environment. And no one ever thinks to try and draw lessons from that failure of unitarity and other effective theories about the character of an underlying deeper theory, for very good reason. So what is different about this case? Almost everyone seems to think we should be able to draw really profound lessons about the nature of an underlying theory of quantum gravity from a solution to a problem proposed in the context of an effective theory. So that's my challenge. And I am now very much looking forward to the presentations. Who's going first? Anyone?
Am I the first to start?
Is it the volunteer or is it?
You are now.
Okay. Let me turn some slides on and start my 15 minutes chronometer. I want to stay on the time. Start at 13. All right. So thanks a lot. I'm super happy because I've been struggling a lot with a so-called information paradox or information problem. And I am very much just at first reaction sympathetic with what our moderator just said, Erik. I don't see an information problem. I don't see an information paradox. I don't think there is any. I don't think there is anything particularly deep to learn from it. Or more precise, this was the second slide, actually. The first slide is this one. The black hole information problem is a false problem. And that was my second slide, which make it sharpen a little bit. Resonating on what Erik just said, I think there are different things that people call the problem or the paradox. I'm going to talk about 3. Erik mentioned 5. I think that it is a problem or a paradox only for that sub-community which is exploring a certain hypothesis, which is some in short or vaguely some short version of holography. It's a community of ADF CFTs, Raju community. It comes things like that, and which adds to established fact about nature or well known or well-supported fact about nature, an extra hypothesis, and this is extra hypothesis that create a paradox and a problem. So I think it's a problem for that hypothesis. I'm going to argue for that, and I would argue for that, trying to clarify that there's a lot of confusion in talking about the setting. There's a confusion between event horizon and trapping horizon. There's sometimes an assumption that there is an event horizon, and that may be false in quantum gravity, it's killing half of what comes after. There's a confusion between timescales, the timescale up to the end of the evaporation and after, what happened after. There's a confusion, and there's a key confusion, which I'm going to articulate, between the thermodynamic entropy, which is sort of the quantity we introduce to make sense of the exchanges between heat and work with a certain system, and the von Neumann entropy, which measure also the entanglement between, say, a system and the exterior, and us, for instance. There's a confusion between boundary states and bulk states of a black hole, and there's a confusion between different versions of holography. Weak, in some sense, there is a holography in the world. It doesn't mean there is sense in a stronger sense. Let me start with what we mean by black holes, because that's part of the confusion. There's somebody who says a black hole is the physics of whenever there is an event horizon. That seems silly to me today, because we don't know whether there is or not an event horizon because of Hawking evaporation. I'll say it in a moment. So one can define a black hole with a parent horizon, a trapping horizon, or more reasonably now, unlikely 15 years ago, we have all this empirical evidence of stuff out there, which seems to be very well described within certain approximation and scales by certain Einstein metrics, and that's what black holes are, those things there. Now, those things there approximately describe a Kruskal metric, but only a part of the Kruskal metric. Of course, only the exterior and the do you see the, let's see, do you see the,
yeah, we can see the cursor and the slides.
little cursor. Okay, so the exterior and the interior of the black hole, but of course not the singularity itself, because the singularity itself, I would say almost all of us are completely convinced that is not described by classical relativity, because something else happened there, because quantum theory takes over. So the reliable part of the Kruskal or the Schwarzschild or the Kerr or Kerr-Newman or whatever metric, it's only, so this is a star, this is the horizon, this is the exterior, this is the interior of the black hole, this is just Schwarzschild. It's only physically reliable, of course, when the curvature is it's much less than a Planck scale, so Planck length to the -2, which means carefully, not just inside within the curvature, but also outside, if there is Hawking radiation, because the horizon, say the trapping horizon, shrinks. And so when it shrinks, it becomes Planckian. The curvature outside becomes Planckian, which means that everything in the future of that is affected by quantum gravity. So either we ignore quantum gravity, and that's not in the game, or we keep into account of quantum gravity, and then we have to say which hypothesis of quantum gravity we are following. Now, of course, I think most people here is familiar with that. An event horizon is the boundary of the past to future infinity. A trapping horizon is sort of local or quasi-local, just the reason where the area of outgoing null surfaces decreases, so you cannot escape for a while, but you can escape in the future if something violates the Einstein equations, of course. Physical black hole, all the evidence say that they have trapping horizon. No argument is on the table whatsoever for saying that it's an event horizon, because there is Hawking radiation, and because we have to go through a quantum gravity hypothesis to say where there is. Now, there are two versions of the many that Erik mentions of the black hole paradox. The first, let me go back, say to, I should put this somewhere else, to this picture here. The first is completely trivial. The information on Sky Plus if this is the Penrose diagram of physical space-time, is insufficient to get the information on SCRI minus. Well, that's completely trivial. Of course, information has fell into a black hole. So why should anybody be surprised about that? That's an old point made by Walt, by Unruh, by many people. So the naive version, oh my God, we lose information, is just silly. But that's not the version that raises worries for some people. The version that raises worry for some people has nothing to do with what happened in the blue region. It can be played entirely before quantum gravity. So in a regime in which we ignore quantum gravity because we are before the quantum gravity region. So now if we assume that the geometry is given by naive background back reaction of the Hawking radiation, so the horizon shrinks, and quantum field theory of space-time, people argue, let me say this strongly, people argue wrongly as follows. The area of the black hole shrinks, therefore the Becker-Hawking entropy shrinks, therefore, this is the mistake, the number of available states diminishes because the number of available states is given by the entropy. The von Neumann entropy has to increase if we believe that the outside Hawking radiation is not pure because it's entangled with the inside, but at some point it has to come down because there are not enough states inside the black hole. Okay, that's a standard argument for the black hole information paradox. And that's wrong because it assumes the von Neumann entropy has to be less than the thermodynamical entropy, which is a mistake. Okay, the thermodynamical entropy is just a number of states you have access to in the interactions in which you exchange heat and work. The von Neumann entropy is that case, if you have a pure state between the outside and the inside, you trace on the outside, or you trace on one of the two, and you compute the von Neumann entropy of the other. Now, it's very easy to, anybody in condensed matter physics knows very well that there are situations in which the von Neumann entropy can be higher than the thermodynamical entropy, and this is a typical example. You have a system A, which contains a smaller system inside, which is isolated for a while, for a certain period. So you might get entangled with A and also B. So your von Neumann entropy is maximized by the number of degrees of freedom of both A and B. But since B is isolated, your thermodynamical entity is only determined by the number of degrees of freedom of A. And that's exactly what happened in a black hole. If you're outside, before the quantum gravity region, if you're outside, the thermodynamic entity is determined by these degrees of freedom here. This has nothing to do with the fact that the outside can be entangled with the inside, so the von Neumann entropy can be higher. Okay? So if we want to stay before the quantum gravity region, there is no problem whatsoever. I mean, there is no reason for which the outside observer before, so not forever, has all the information because there's something in the future, of course. Now, what about the future? Well, as everybody knows, Hawking drew this Penrose diagram early in his work, but Hawking was saying that's of course not reliable because we don't know about quantum gravity. We don't know what happened here. That's a much more reasonable expectation. That's in fact just as a side remark what is suggested by a number of calculations in loop quantum gravity and in other approaches. So the Penrose diagram has no event horizon. There's a trapping horizon. Everything is just as before up to here, but then the metric here doesn't. The Einstein equation are violated in a region. So if you want, you can have an effective metric, but it doesn't satisfy the Einstein equations. And the information that falls inside is recovered just outside after that. There is nothing that violates that, unless you make strong hypotheses, like what Juan Maldacena called the dogma which limits the number of possible black holes once the area is small. But these are problems of those who believe in ADF-CFT, those who believe in certain approaches to quantum gravity, not problems that come for anybody who does quantum gravity in any other reasonable way, like do quantum gravity or others, or anybody who just considers us reliable quantum field theory and curved space-time and simple hypotheses about quantum gravity. So the early observer doesn't have all the information, just because some information that falls in get to the late observer. The theory is unitary, Sky plus and Sky minus connected to one another. The Einstein equation are violated in a small region because of quantum effect. I don't see where is the problem. Now, this can be, if I have a couple of minutes more, helped a little bit more by just looking exactly what is the geometry inside just before entering the quantum gravity region. Just, classical GR. It's a very, very large volume region inside, this one, which is small in radially, but very, very long in the internal direction. So it's more angularly, but very long in the radial direction. It's very long. So it's a small region since outside with a huge volume inside. And of course, this is the confusion. This is classical GR. Everybody's confused about that. A small black hole, which is old, evaporated, and a small black hole, which is just collapsed with that same mass, are totally different inside. So two black holes with the same mass and charges are equal as seen by outside, but are different as seen outside. They're different systems. So this idea that all black hole, the physical black hole is just determined by mass and charge or angular momentum, just wrong once you have to take into account the information inside. One can prove, and this is a paper of mine, but I want to make a remark here. I'm not presenting my own view of the problem here. It's a view of the problem of a large part of the community, everybody doing quantum gravity, general relativity, classical general relativity, and does not fall into the black hole of ADF, CFT, supersymmetry strings, and that kind of things. That's where the problem is, not in GR and not in quantum mechanics by itself. What I was saying here is that you can prove strongly that if quantum field theory, you believe quantum field theory in the region of small curvature compared to Planckian, necessarily the number of degrees of freedom inside does not decrease. It's a fact. I'm not going through the argument. So what about the belief of the rest? Well, if you look at the people who do things properly, like this is Polchinski, Marov, this kind of people, and you look at the postulates, they make a postulate which explicitly contradict quantum field theory. It is in their paper explicitly. So the black hole information problem is a problem of those who add to our understanding of quantum field theory and curved space-time, our understanding of back reaction, more or less naively, our understanding, or at least my understanding, the quantum gravity community understanding of quantum gravity, adds some extra holographic belief, hypothesis, which I am not God, but I'm not convinced by it. So I want to just conclude. Unitarity and equivalent principle are compatible, contrary to what the people say there is a paradox or a problem. Confusion, it's all over between event horizon, entropy horizon, thermodynamical entropy for Neumann entropy, boundary states, internal states, time scales, and stationary or evolving black holes. This is a reasonable picture of what happens. There's a large literature describing what happens. The information comes into the black hole, passes the other side, exits a white hole. The black hole is large, becomes small. The white hole is always small from the outside, but is large from inside. Energy is conserved, information is conserved, everything is kosher. Nothing is violated. What is violated? It's a strong holographic hypothesis, or the eternal exact validity of the generalized second principles of thermodynamics, Bekenstein, as opposed to the approximate validity in the region before the change. So I go back to my initial statement. The black hole information problem, it's a false problem. There's no paradox whatsoever. It's only a problem of those who add an extra hypothesis, Maldacena dogma. It correctly is dogma. I talk a lot with Juan. He agrees with that, with what I said. If you believe in that, because you have other reason to believe in that, you're a problem. But I think it's a problem for that hypothesis. It's not a problem in quantum gravity. It's not a problem in classical gravity. Not a problem in curve theory on space-time. I have some, reference, but I'm finished, and I'm 15 minutes or something.
So thank you very much, Carlo. That was marvelous, and as we always expect from you. And in fact, you came in at almost exactly at 15 minutes. So thank you very much for that also. So who would like to go next?
Could I go next?
Yeah, Suvrat, please.
Okay, great. Just 1 second, please. Yeah, let me share. Oops. Sorry, having some trouble sharing. Yeah. Okay, maybe I make this full screen. Yeah, can you see this?
Yes.
Okay. So thank you very much to the organizers. As I was, thank you very much, Erik, also for that, for the introduction and for setting this off. As I was saying to some of you who came earlier, I'm sorry, I apologize for the quality of my Wi-Fi connection. I committed some mistake in connecting to the Wi-Fi, and as a result, I've been banned from the Wi-Fi in the institute in Moscow where I am. So I'm on mobile internet. I hope you can hear me, but if you can't, please just let me know. So thanks also, Carlo, for explaining your position on this. I have to say before I start that, there are several comments that were made about the dogma and holography and so on. And I'm going to use some of the same words, but in fact, my position is slightly different from the position of maybe, some others who work in this field from the string theory community. So I just like to say, what I'm going to say, and I'm happy to discuss more some of the differences that I have also with others who are maybe part of the same community. In fact, let me start by addressing the point that Erik made at the beginning, which I think is an important point, which is the question of, what we mean by the black hole information paradox. And I think that, there are several versions of the paradox. There are some that we understand well. And I think the ones that we understand well are the ones that Hawking originally formulated, and those are the ones I want to speak of. And it's true that there are other paradoxes about black holes that are called the information paradox, but those are different. So indeed, I wanted to start by explaining what it was that Hawking at least meant when he talked about the information loss paradox. Indeed, Hawking's point was, Hawking, of course, had a computation of Hawking radiation. But the computation of Hawking radiation doesn't lead to a paradox, which is something that Erik also pointed out at the beginning. Because, the computation of Hawking radiation in the end is a computation of a two-point function. And a two-point function cannot really distinguish a pure state from a mixed state. Those two can be exponentially close. So that's a coarse-grained observable. But in fact, Hawking had a more sophisticated argument which led to information loss, and it was an argument that was based on causality. And so I think it's useful to recap what that argument was, just so we're on the same page. So Hawking's point was, if you look at where the Hawking radiation originates from, it originates from the exterior. And then he said, the exterior has no information about the interior except for the mass charge and angular momentum. And therefore, if you look at the observer on Scri+, the observer on Scri+ must trace out the interior, and that leads to a mixed state. Yeah, and in fact, what I'm saying here is almost an exact paraphrasing of what Hawking said, and it's useful to just go look at his paper. In his paper on information loss, he introduced what he called the principle of ignorance. And this is really, on the left, a screenshot from his paper. And it's a very important part of his abstract. And what he says is that about every black hole, one must introduce a hidden surface. A hidden surface is what in modern terminology we would call the interior. And he said, all field configurations on these hidden surfaces are equally probable, provided they're compatible with the conservation of mass, angular momentum, etc., which can be measured by surface integrals at a distance. Yeah? I know Carlo spoke about how there might be even more degrees of freedom inside that might be invisible to an observer outside. But the basic assumption that Hawking was making was that you had these degrees of freedom inside the black hole that were invisible to an observer outside. And that's an assumption that's, of course, true in quantum field theory in curved spacetime, which was alluded to also a lot in the previous talk. But that's just wrong in quantum gravity. It's just demonstrably wrong, as I'm now about to explain. Yeah. So the first point I want to make, and this will also, later lead to the second question that Erik asked about what we learn about quantum gravity. The first point is that this idea that you have a principle of ignorance, which is that you have a no-hair theorem, that from outside, all an observer can tell is the mass, charge, and angular momentum. That is false, okay, and that's demonstrably false. You can, and I'll explain a little bit more. An observer from outside can tell a lot more than the mass, charge, and angular momentum. And in fact, for a black hole formed from collapse, has complete access to the microstate of the black hole. And in fact, in a theory of quantum gravity, rather than a principle of ignorance, we have what one might call a principle of information, which is that the complement of any bounded region, and black hole is a bounded region, has all information about the state. This is something that's true in asymptotically flat space, in asymptotically anti-de Sitter space, in asymptotically de Sitter space. We call it the principle of holography of information. It should be distinguished a little bit from the ADS-CFT conjecture. This is, of course, consistent with ADS-CFT, but it's more general because this works also in asymptotically flat space. It's also slightly weaker because this is not a statement that there's a dynamical dual, but it's the statement that information about any bounded region is available outside. I want to explain that a little bit more. And in fact, I think that the reason the information loss paradox is so interesting is because it teaches us this profound effect about quantum gravity. And the way it teaches us this effect is not even that, information loss is crucial to argue for this effect, but because it's by thinking about information loss that we learned about this effect. And this, I think, is really something deep about quantum gravity that's of interest, and it's of interest independently of black holes. It's just a fact about quantum gravity, which I'll try and persuade you about at the end of the 15 minutes. I want to make this point once more, and I want to explain once more what this means. Yeah. So let's just think a little bit about how things work in ordinary non-gravitational theories. In ordinary non-gravitational theories, we can think of a state which has some excitation. Can you see the cursor maybe? Okay, so I'll assume you can see the cursor.
Yeah,
So which has some excitation inside this bounded region, and it looks exactly like the vacuum outside. The way you create such a state is you act with a local unitary operator inside this region. Of course, you can act with another unitary operator, which changes the excitation inside this region, but still leaves everything outside looking like the vacuum. That's the situation in a non-gravitational theory. Now, if you think of classical gravity, you see that's already wrong, because the moment you put something inside this bounded region, the classical Gauss law tells you that there has to be a tail outside, so the observer outside can measure the mass. However, and this is the situation Hawking thought, black holes were in, which is the situation on the bottom left, that, you can tell the mass and the angular momentum from outside. However, in quantum gravity, we have a stronger statement. In classical gravity, you can redistribute the mass here, in such a way so as to keep the external integrals constant. But in quantum gravity, the claim is, and this can be shown under rather general conditions, that if you change the distribution inside the bounded region, you also change the tails outside. So an observer outside has, provided the observer outside makes sufficiently accurate measurements, and I can quantify that, has access to all the information that's inside. So the error in Hawking's argument was to believe that we were in the bottom left situation. And the error in a lot of quantum field theory and curved spacetime arguments that are made to argue further scenarios is to not take seriously these features, which really follow from the constraints of gravity, and one can't get around them. So I want to now explain these features a little bit, and I want to focus your attention on the bottom right feature. And the point once again of this cartoon is to say that an observer outside knows everything that's happening inside, not just the mass, charge, angular momentum. Yeah. In particular, what this means about the information loss paradox is that if you make sufficiently accurate observations outside, so if you think of the wave function of the exterior then that wave function of the exterior has all information about the interior. It doesn't have only mass, charge, and angular momentum. As a result, of course, the Hawking radiation that's formed in the exterior is also sensitive to what's happening in the interior. And the idea that the Hawking radiation only knows about a few parameters is only a coarse-grained, is only valid in a coarse-grained setup. And if you were to make an accurate computation of what's happening outside in these, you can't exactly compute the Hawking radiation, but you can compute the entanglement entropy. Then that would show that that radiation has access to everything that's inside. Yeah. So now, these are results that can be, as I said, these are some cartoons, but there's a rather precise result that can be proved. And the precise result is as follows, and I'll explain how it relates to the previous pictures. It's to think of the algebra of operators on Scri+. Yeah? So the reason we think of Scri+ is, of course, because in gravity, it's always easy to work on an asymptotic slice rather than to work on a slice which goes through the bulk. Here I'm happy with the idea that the black hole has evaporated. So this Penrose diagram for me includes also states which had black holes in the bulk, which later evaporated. In a non-gravitational theory, if you think of the set of independent operators in this setup, they comprise distinct operators at different values of the retarded time. So, you have independent operators. And if you think of Scri+ as being the limit of, Cauchy slices pushed upwards, you can think of these operators as being operators in the bulk, which are all independent. One can prove, using rather weak assumptions about the UV complete theory of gravity, that in a theory of gravity, every operator on Scri+ can be approximated arbitrarily well by an operator from its past boundary, which is this red region here. And there's a similar result one can show for Scri-. This is really a proof in some sense of the holographic principle, and it's made without assuming something about string theory. It's made assuming just rather weak assumptions about the theory of quantum gravity. And it's a statement that doesn't also require an assumption that we are anti de Sitter space, because I'm stating the result in flat space. I don't have time here to go through, the proof of this, although I'm happy to go through it in the discussion. But I want to discuss, some features of this result and also give you some intuition for it. Yeah. So this precise result that I spoke about, which is in fact the setup that applies to black holes, it's a non-perturbative result, and it's subject to some weak, but I think very reasonable assumptions about the UV complete theory of gravity. One can also ask, that people do quantum field theory in curved space-time and classical gravity, and surely they're not completely wrong, and of course they're not completely wrong. So indeed, if you coarse-grain your observations a little bit and you construct what are called relational observables, you will recover ordinary notions of locality in the QFT limit. So this result doesn't tell us that, the world around us, everything is holographic. Clearly, at this moment, to a very good approximation, I'm locally in this room and my co-panelists are in different rooms. And that's fine. That's because we are making coarse-grained observations. But if you make very precise observations, then, you find that information is localized differently. But most interestingly, and I think this is the key point, the reason all of us should be interested in this issue is that it's not an abstract issue, because holography has very practical consequences even in the perturbative gravity regime. So if we think in the future of doing some experiments to test for quantum gravity, then this, I would say, is the smoking gun feature of quantum gravity. The fact that in the perturbative gravity regime, we can see these signs of holography. And that, I think, is a very profound thing about quantum gravity that we learned because we started thinking about black holes. Okay? So what I want to do in the remaining 4 or 5 minutes is explain to you how holography is important in the perturbative regime. And that also helps to build intuition for this result. Yeah. So, I've been telling you things are holographic and how information is stored in the past boundary. So here's a quintessential example that shows, how this is an interesting feature. Imagine there's some excitation, that's this blue region here, which kind of starts off in the middle of flat space. And this excitation sends out some shock waves that travel at the speed of light, or maybe some light rays, don't have to be shock waves, that go and hit Scri+. Now, I've been telling you that the observer outside this bounded region, and there's no black hole here, this is just excitation about the vacuum, has access to everything that's happening in the bulk. So you could say, well, here is how I created the excitation. It's a simple unitary operator. Here's some matter field, and I smeared it with some function f. This function f has support in retarded time 0 to 1. And now make these observers here do some measurements in near Scri plus minus near the past boundary and determine what the profile of this is, right? So they have to determine what's happening in the future. And you might have thought if you used intuition based on quantum fields and curved spacetime, which was used a lot in the previous discussion, that this is impossible. However, it's very easy to see in perturbation theory that this is possible. And what you need to do is compute a two-point function of the integrated Bondi mass at retarded time minus infinity, or the ADM Hamiltonian, and the same field that was used to create the excitation, but inserted near Scri plus minus. And if you do that, it's a simple computation. You will find that this two-point function has support even near Scri plus minus. You can compute it. It's a simple computation. And you will see that using this two-point function, you can completely read off this function f that happened. So this is how, these people can foretell what is going to come and hit them on Scri plus without having to wait for what's happening on Scri plus. And this is also how you should think of what's happening in the case of black holes. You have observers outside, and they can tell what's inside if they make sufficiently accurate measurements without having to wait for that stuff to come out. Now, it's very important that this idea cannot work without gravity. So if you're stuck to quantum field theory in curved space-time, this idea is just wrong. This idea is also wrong, by the way, in gauge theories. It's wrong in gauge theories because in gauge theories, you have exactly local gauge invariant bulk operators. So if I didn't have gravity and I just had QED, then I cannot tell the difference between the vacuum and the vacuum excited with, small Wilson loop in the middle. These people are out of luck. There's no way they can distinguish between those two states. This idea also doesn't work without quantum mechanics. Yeah? So if you restore the factors of h bar and c, which is maybe the hardest part of this calculation for me to do, you will find that, if you get a factor of h bar g by c cubed. And so if you're in the classical theory, then of course you have Birkhoff's theorem. You recover the classical physics, which is these people can only tell the mass outside, and they can't tell what's happening. They can't tell the profile of what's happening inside. And of course, in the non-gravitational limit, this correlation function just vanishes. Yeah. So this is a concrete example of how people here can read off what's happening inside. I could have given you one more example, which is you could have imagined there were two fields related by a global symmetry, maybe O and O tilde, and we can discuss more in the panel discussion. I'm happy, you can, even these observers, it's not hard to see how they can tell whether it's an excitation of this blue ball or maybe an orange ball, which is just a different field which couples the same way to gravity. So this is a very interesting phenomena because it shows you perturbatively how this assumption that Hawking made, that stuff outside is just, the observer outside doesn't know what's happening inside, is false, and it's false even in perturbative gravity. Yeah. Now, there's an interesting question here, which is a question about locality. You might have worried, you might have said, look, the observers outside, they look like they're space-like disconnected. So how can they tell what's happening in the future? And maybe this is an important point, the last point I want to make. You see, we should be careful because what's happening here, I cheated a little bit in these figures. I drew a figure which suggested there was an excitation which was just originating in the middle. But in gravity, that never happens. Now, the excitation always comes in from Scri minus, and that's also true in the case of black holes. The infalling matter came in from Scri minus. And so the key point is that in gravity, after sending in an excitation, one cannot erase information from infinity. Traces of the information always remain at infinity, whereas in non-gravitational theories, one can. And that's the key reason why Hawking's argument was wrong. And that explains how information emerges from a black hole. This is not a dogma. This is something I just showed you a perturbative calculation. I could have shown you a more clear non-perturbative proof. But this is just something very explicit. And this, I claim, is the key error in Hawking's argument. It's assuming that the information that went out is localized like it is in non-gravitational theories, and therefore the region outside has no information about the inside. But this is demonstrably false, not because of a dogma, but by explicit calculations. And I think this is how we should think of how information emerges from black holes. Okay, so that's all I wanted to say. I'll stop here.
So, Suvrat, thank you very much. And you did go 2 minutes over, but we will forgive you because it was really interesting, great stuff. So thank you for that. Bernard, are you
okay.
Ready to go?
Yeah, let me just share my screen. Yeah. Okay. Can everybody see that? Remarks on the information loss puzzle? Yeah.
Yeah.
Okay. Well, yeah, thanks to the organizers for including me in this fun event, and thanks to the previous speakers. An advantage of speaking last is I don't have any loss of information about what the previous speakers were going to say. anyway, the remarks I've prepared are reflect what Erik actually said at the beginning, that that the phrase information loss puzzle or paradox seems to mean different things to different people. And people also differ, or sometimes I would venture get confused as to whether they regard it as a puzzle about full quantum gravity or a puzzle about semi-classical gravity. So I'm going to list 4 or possibly 5 points of view about what the information loss puzzle is and discuss each of them. One of them is my own statement, but I'll also have some things to say about some of the others. So the first statement, and I've derived this from a paper by Tim Maudlin, a philosopher of physics, Information Paradox Lost. But it's similar to what Unruh and Wald say in their review article. And I think the context of this statement, it takes the view that the information loss puzzle is about semi-classical gravity. Okay, and the statement is that we can't well, I should make reference to this picture, okay, which we've already seen, which appeared in Hawking's 1975 paper already, which I guess you're all familiar with. So bearing that picture in mind, the statement is, we can't retrodict the initial state from the state after, just a minute, your pictures are covering my screen for me, after the black hole has evaporated, because some of the state went into the black hole singularity. And concomitantly, an initial pure state becomes a mixed state in the post-evaporation region. Okay, that's this region here, labeled PE. Okay, and then Maudlin and Unruh and Wald go on to argue that this is not a paradox, though, because, as they say, even though the singularity eventually disappears, from an eternal perspective, the singularity exists, since it once existed, and the lost information is eternally in the singularity. So they would say no paradox. Okay, so that's one version. The next version, which I've adapted rather freely from the ICEP 2022 status report by Fernando Quevedo, but it essentially reflects the recent mainstream focus of people who work on what they call the information loss puzzle. And the statement is this: Hawking radiation with density operator rho has entropy given by the von Neumann entropy, SR, R standing for radiation, minus trace of rho log rho. SR might be expected by Hawking's calculations to increase monotonically, but if the excuse me, if the total system starts as a pure state with zero entropy and the black hole completely evaporates and unitarity holds, then at the end the total system consists just of the radiation, so SR should go back down to zero. So the puzzle is, how can you understand that happens? And I should say that this puzzle in itself is a puzzle about, you can regard it as a puzzle about full quantum gravity, but I think what makes it a puzzle is that typically what people expect of a resolution is that it will involve an understandable semi-classical picture about what is happening and how this SR goes back down to zero. Okay, so then I've also included 2 statements which Suvrat quotes himself in his Physics Reports article, which he mentioned, or the first one of which he mentioned. Hawking showed, so I'll read these very quickly. Hawking showed that a black hole emits radiation that depends only on its mass, charge, and angular momentum. This leads to a paradox with the unitarity of quantum mechanics, since it suggests that the process of black hole formation and evaporation leads to loss of information about the initial state, except for information about a few conserved charges. And then there's the statement that Suvrat also quotes at the beginning of his review article, string theory shows that the evolution of the black hole must be unitary, but we do not know the precise mistake in Hawking's calculation. To which I would only add that I don't think it's just that the people are just worried about finding the mistake in Hawking's calculation, but after all, why aren't they happy with the statement, well, quantum gravity just is unitary, and so SR does go back to zero. I think the puzzle for many people is that they want to reconcile that with an understandable semi-classical picture. Okay. And lastly, I want to tell you what I have always thought the black hole information loss puzzle is, and I think this really is the puzzle that remains if you don't ask for a semi-classical understanding, but you just assume that quantum gravity is a standard type of quantum theory, unitary, and that somehow or other black holes evaporate. And for me, the black hole information loss puzzle is really just a special case of what I would call the second law puzzle. What we think of as lost information in the case of a black hole evaporation is really just increased entropy. Here I mean thermodynamic entropy. And the puzzle is how to reconcile the increase of thermodynamic entropy of a closed system with the unitarity of quantum mechanics. And this is a problem not just for a black hole, but for any closed system. It's a problem for the universe if you believe that after the Big Bang, as the universe evolved, its thermodynamic entropy increased. And it's just that the case of an evaporating black hole particularly throws this puzzle into relief because the black hole is the one system where we think we know without any ambiguity what its entropy is, right? And the problem arises, I think, from the explicit or implicit, but anyway, presumably mistaken assumption that we identify the thermodynamic entropy of a closed system with its total von Neumann entropy. The problem being that von Neumann entropy is a unitary invariant. So how do we resolve this puzzle? And you know, in general, how do we understand the second law of thermodynamics? To resolve it, I think we need to seek a new definition for the entropy of a closed system. So a closed system could be the system consisting of a collapsing star in an otherwise empty, asymptotically flat universe, or it could be the whole universe, okay? How do we seek a definition for the entropy of a closed system, and I want this definition, first of all, to be objectively defined. So you see, if I could digress for a moment, so much recent work on the information loss puzzle seems to take for granted that the standard point of view about statistical mechanics, which is based on the idea of entropy of a closed system being defined by coarse graining, it takes for granted that that is an okay understanding of entropy. And I think one lesson we learn from the Hawking effect is that maybe entropy is not because what I should have emphasized is the standard view of entropy based on coarse graining is partly subjective and partly vague. And there's nothing vague about the area of a black hole. And this is a point that was made frequently by people soon after Hawking made his discovery in 1974. I can if there's time later, I can show you a quote by Roger Penrose on this point, but seems to have been forgotten. That I think we should be dissatisfied with the standard understanding of thermodynamics and the second law, and we should take the existence of the Hawking effect as an opportunity to rethink the foundations of thermodynamics. So to resolve this we seek a new definition for the entropy of a closed system, which is A, objectively defined, and B, obviously, it has to not be a unitary invariant, and which will plausibly increase with time. Okay, so I'll come to my proposed solution to that problem, but let me return to all these four puzzles and briefly discuss them all. So let me say, first of all, what constitutes a resolution to the information loss puzzle depends on which version one focuses on. Moreover, even when they agree on the statement of the paradox, different people or research communities tend to speak in different languages, and this can mean that even when two communities are proposing what is essentially the same resolution, or where there are at least overlaps, it is not always easy to appreciate this because they are often couched in different languages. But anyway, let's turn to the statement A, which you remember was due to Maudlin and Unruh and Wald, who have already said they argue there is no paradox. They just say information is just lost in the singularity. But let me mention an arguably more satisfying resolution is argued for by Benito Juarez Aubry, who introduced us this afternoon in this paper in Classical and Quantum Gravity in 2024. And Benito conjectures that actually there is no semi-classical solution whose space-time looks like that in this, in this figure. Because, he conjectures, any initial Hadamard state will inevitably be singular on the Cauchy horizon of this point n in the figure. Let me go back to the figure, which, as we all know, is a naked singularity. It's not really in the manifold, okay? But the point has a Cauchy horizon indicated by this sloping line here. And Benito's conjecture is that any initial Hadamard states in the initial globally hyperbolic region to the past of that Cauchy horizon will necessarily become singular on that horizon. And so there is actually no if his conjecture is correct, which we still think it is, there is no semi-classical solution that looks like that picture. If you want to have a semi-classical solution related to your initial Hadamard state that you've chosen, its space-time will terminate at the Cauchy horizon, so it will look something like that, okay, but with no post-evaporation region. Okay, so the post-evaporation region is simply not there, and there's nothing paradoxical about that. But of course, as Benito also indicates, we don't believe for a moment that the post-evaporation region is not really there. Instead, the true lesson of this is that you can't resolve the information loss puzzle within a semi-classical framework. And presumably, as he also says, and by the way, as Carlo essentially said in part of his talk, in the true quantum gravity solution, there is no singularity, and to the extent one can describe things with a space-time picture, it looks more like this, which is a bit similar. There are important differences, but a bit similar to the picture that Carlo showed us in his talk. So you have a globally hyperbolic, something that, you know, you can't really represent a quantum gravity solution with a space-time picture, but to the extent that you can, it will look something like this, but there'll inevitably be a non-semi-classically describable region as shaded in this thick black curvy bit here. Okay, so so that's my discussion of statement A of the information loss puzzle. What about statement B, which was about the von Neumann entropy or fine-grained entropy of the radiation going back down to zero? Well, let me just say, it's unfortunate we don't have a representative of this, what one might call mainstream version of the information loss puzzle, but let me just say much progress has been made towards resolving this version in terms of a long story, still unfinished, partly controversial, by these authors and many others. Apologies if I've missed, for all the people I've missed out of that list, which I won't attempt to retell here. But just to remind you, it involves the notion at the quantum gravity level of replica wormholes and at the level of a semi-classical picture, because this work, if I understand it, is done in order to provide oneself with a semi-classical picture. They do this with the notion of minimal surfaces and islands, etc. And they argue that SR does indeed tend to zero at late times, as Don Page indeed anticipated with those assumptions that Carlo has questioned, his so-called conjectured anorexic triangle hypothesis and the Page curve story, and as Leonard Susskind also predicted, and others with their so-called fast scrambling hypothesis. But I won't say any more about that. The other statements were in Suvrat's article, and I assumed, well, he has discussed them, I guess. So let me finally turn to my statement that what I consider, wait a minute, sorry, let me go back to, yeah, my claim statement of the black hole information loss puzzle, but it's really just a special case of the second law puzzle. I argue, by the way, how am I doing for time, Eric? I've totally lost track.
So you are now at 17 minutes. So I would ask you,
okay.
I would ask you to wrap it up quickly, please.
This is my last view graph. Okay.
Wonderful.
Apologies about that. So I argue, from its seeming ability to resolve the thermal atmosphere puzzle, so I can talk about that in the discussion perhaps if people want me to, that the right definition for, because remember, for me, a resolution to the puzzle is to give an objective definition for what we mean by thermodynamic entropy. The right definition is matter, gravity, entanglement entropy. And then I argue that if the initial state, and this could apply to the universe, if you're thinking about the second law, or it could apply to a collapsing star if you're thinking about black holes. If you make the additional assumption that the initial state has low matter gravity entanglement, then this entropy defined in this way, which of course is not a unitary invariant, will plausibly increase. So the question of whether the second law holds actually becomes an objective question about the nature of the, if you will, the quantum gravitational Hamiltonian. And just very quickly to mention, and you can read about this in these papers on the archive, and one of them is also published. One of them is a shorter version of the other, by the way. A prediction is that the final state of Hawking evaporation for an initially large black hole will consist mostly of a roughly equal number of photons and gravitons entangled with one another. Okay, sorry to be over time, but that's the end.
Well, thank you, Bernard. And actually, just as for Suvrat, we will forgive you for being late, because it was that was really wonderful. Thank you very much. So because we're running a little bit late, I'll go ahead and throw the floor open. Except I'll reserve the first 3 questions for the panelists themselves if they want to ask questions to the other panelists, and then I'll throw the floor open to the audience. So Suvrat, Carlo, Bernard, do any of you want to viciously destroy one of the other panelists?
Yes, but not visually destroy, make a comment.
Okay, yeah, I had a question too, but go on, Carlo.
Just secretly undermine.
I have 2 or 3 very short comments. The first, can you put back the slide, Bernard, the picture, the Penrose diagram that you like?
The Penrose diagram that we like, this one.
No, the one you like, this one.
This one.
Yeah, no. This
The
one
the
you like.
standard one.
Yeah, no. The colored one, the one in colored. You just
This one.
the
that one, right there.
No. Probably there's a delay. So when we say yes, you're right that there is a similarity with what I'm suggesting, and I know your work. By the way, I like very idea.
Well, this
very
is
much.
Benito's work, I should emphasize. Yeah.
It's very. I like the idea of the gravitons and sort of photons entangled. I don't have time to go into that, but I want to make a comment about this diagram here. The black region is where you expect funny things happening from the classical point of view.
Mm-hmm.
Now, what I want to emphasize is a technical point, which is the following. I mean, of course, we can describe certain quantum phenomena, not gravity, quantum phenomena, just as violations of the classical equation of motion, right? If you have say, tunneling, there is a possibility that a particle goes through a wall, a potential barrier, just because it violates energy conservation for a short while, and then it continues. So nothing prevents us to imagine that we can describe what happened with a metric, a classical metric, that in some region we just take as a effective metric where there is a quantum gravity phenomenon, which is just violating the Einstein equation. Now, what I want to stress is that there is a solution of Einstein equations, exact solution of Einstein equation, that allows you to draw this Penrose diagram where the black region is only the horizontal part without the part that goes all the way to square plus.
Okay, without this bit.
Yes, without this part. In fact, one can show, this is a technical result, that there is you can do an exact solution of Einstein equations in which you have the exterior, the black hole. On the other hand, the other side, you have a sort of white hole solution. There is an anti-rapid, and the violation is only sort of inside the horizon, of course, a little bit outside the horizon, but not going far away, which makes this possibility, in my opinion, much more plausible. That's a quantum gravity, as you strongly insisted. So I think any attempt to understand what happened to the information inside without addressing quantum gravity, without addressing specifically what happened at the end of the evaporation, it's unsatisfactory because, and that's my second comment to Raju. In a sense, Raju, you never discuss the paradox. You offered a solution, assuming there is a paradox, okay, and saying, well, I have a version of quantum gravity. You said weak assumptions about the ultraviolet completion. I studied your papers. You remember we met at a conference. You tried to explain me all this, and then you gave me all the literature. I went home. I did my homework. I studied your paper. People were very excited about your result. Of course, I know many people appreciate. I don't understand this result. I don't buy the result. I think there are some things which I would love to discuss you more, not here, of course, in technical. But more importantly, it's a non-solution to the problem, because if we are discussing of what happened before the end of the evaporation, quantum field theory is perfectly okay. Nothing. Why do we need to change it? If we want to ask what happened at the end of the operation, well, let's discuss what happened at the end of the operation. and then we need a full quantum gravity calculation. And I know people who work on it. I know attempt to this, just making a very wild hypothesis, which of course everybody loved because everybody fell in love with holography. This idea that you can measure things at infinity and exactly know what is inside, I just don't see it, I don't buy it. Every time I go into the technical details, I have difficulties. So I think, independent of my difficulties, but it could be me not understanding the technicalities, of course, that's very possible. But it's a known problem. Either it's a question about full quantum gravity. So what happened at the end of the evaporation? We did a calculation. That's what I know a lot of people are trying to do with loop quantum gravity, numerically, with other ways. So that's a good scientific problem. Before that, to say, well, since we assume that something is happening in quantum gravity, we have a problem about unitary conservation. Therefore, something very strange has happened. So I try to model it with a calculation. It just doesn't seem right to me.
So, Bernard, do you have anything that you'd like to say in response before I go on to Suvrat? Do I just have something to say in response?
Yeah, well, Suvrat and Carlo have raised a lot of points. Carlo's point about there is a what was your point? There is a classical solution of Einstein's equations that looks like this with this black region, but without this black region.
That's correct. I can give you the exact references.
Okay, please do. Yeah, I don't know. Maybe
it's very astonishing because you might think that it's forbidden by Birkhoff theorem, but it's not, because Birkhoff theorem is local, and so this is a the solution is sort of locally but not globally equivalent to Kruskal, say.
Yeah, I don't know if Benito would like to respond to that. As I hope I emphasize this is Benito's picture, but I rather liked it and wanted to. I thought it was definitely something to advertise.
What you call Benito's conjecture? I mean, there's a lot of literature on that, so it's not.
Well, he references the literature in his paper. Yeah,
okay,
for example, the Hawking-Stewart Thunderbolt.
No. We have explicit calculations in loop quantum gravity.
In loop quantum gravity. Okay.
Explicit metrics and effective metrics that describe what may happen.
Okay.
I'm not saying that.
Benito, do you have something that you would quickly like to say?
So I mean, the point of drawing the that thickened region all the way to Scribe plus has to do with the fact that in this region, the solution certainly does not look like semi-classical gravity. So I believe that you can write a solution where there is a black region that is, let's say, bounded around the well-known black hole singularity of the middle. Let's say, assuming this is something like Schwarzschild, right? Because in Kerr it would look something completely entirely different.
Yeah.
In this simple setting, right? And so I mean, and I don't really feel strongly about that, but the fact is that if you believe in something like instability of Cauchy horizons in the semi-classical regime, it must be a deviation of this sort from semi-classical gravity. So it's not really, is nothing deeper than that observation.
By semi-classical gravity, you mean what?
Of semi-classical gravity, because this is the sense in which we typically formulate information laws, right? This is the language that Hawking was speaking in his original paper when he drew that post-evaporation region. So for me, this is the...
You mean quantum field theory on a given space-time?
No, I mean back reacting on a space-time. This is what...
G mu nu is the expectation value of T mu nu.
That's right, yeah. Because this is what Hawking uses to argue for evaporation. He doesn't just do quantum field theory in curved space-time. He goes a bit further and says, suppose you're in the semi-classical regime, then this is... If you don't do semi-classical gravity, you will never get that post-evaporation region. You will just get...
Right.
You'll just get some thermal radiation of Scribe plus.
Right. So, of course, we're not capable of computing...
Carlo, I would like to move on. Let Suvrat have a reply if you like, and then open the floor to so the audience has a chance.
Could I also briefly, I had a question also for Suvrat, if I could.
Oh, I'm so sorry, Bernard. Yes, of course.
very briefly, yeah. So I appreciate very much your, and I've only read about it recently, your Suvrat's point about all the information about the gravitational field being on the boundary. Okay, if you're talking about and I understand it's not a hypothesis, it's a theorem, I guess one could say. I was just, I mean, in a sense, what you're saying is there are no local observables except on the boundary. But of course, you know, as you know, you can also do quantum gravity in a closed universe where there is no boundary. And then, of course, the statement is there are no local observables at all. And of course, there is a very interesting line of research recently about people, especially by people who do AQFT, going back to a paper, I think in 2017 by Friedenhagen and Reisner, where you solve this problem by looking at what they call background independent approach, also known as relational approach, where you say that you ask about the not the value of a quantum field at a point, but the value of a quantum field where another quantum field has a certain value. Okay, and this has been developed in quite a sophisticated way. So, for example, there are papers by Marcus Fröbe and collaborators calculating, what was it? The magnetic moment of the electron or something. Anyway, they do gravitational corrections to that. They do serious calculations in this framework. So Suvrat, I noticed you mentioned a relational approach, but I just wondered if there is a way out of, you know, if you think this would be, how can I put it, relevant to the information loss puzzle, to adopt a relational approach.
Okay. Thanks.
Suvrat, I will ask that you try to be brief. Thank you.
Yeah, I'll be brief. I just wanted to respond to various questions that were asked. In fact, the first thing I want to say, Bernard, is there's a small point of order in the quote that you had from my review. I went back and looked at it. That quote actually said that popular descriptions of the information paradox commonly involve these 2 points. And then the next line says, the purpose of this is to show that these descriptions have subtle errors in them. So that was not my viewpoint, but my quoting popular descriptions and then criticizing them.
No, I understand that. I apologize if you feel I misrepresented you, but I mean,
no, just a clarification.
Trying to say what different popular statements are out there.
That's right. Thanks. Yeah, I just want to say that wasn't my position. The other point I want to respond to Carlo here. I think Carlo said repeatedly this, these results are a dogma or there's a problem with the assumptions. But I think, it's important scientifically to say what the problem is. As Bernard said, this is basically a theorem, and the assumptions that go into this are, I can just state them here. It's the fact that energy is positive. It's the fact that a version of the Gauss law holds in that, if you measure the ADM Hamiltonian at infinity and find it's 0, then you're in the vacuum only. So, at least at low energy states, there's a version of the Gauss law. And the fact that you're in a Hilbert space, which is formed by starting with the vacuum and exciting it with asymptotic operators. Those are the assumptions that go into this.
That's exactly the holography.
Could I complete, please? Could I complete, please? This is not holography. This is the statement that you start in the vacuum and you excite at arbitrary times in scry minus. This is the in and out Hilbert space. It's Abhair's Hilbert space that Abhair Stecker had using asymptotic quantization, and you're in that Hilbert space. And with those assumptions, you find this result. It's a result about asymptotic algebras. It doesn't hold in quantum field theory. And the reason I gave the perturbative arguments was those are calculations we can just do right now. Everyone can do. So I feel that if one is going to say this is an assumption or a dogma, then one has to find some mistake here. It's not sufficient to say there's an assumption or dogma. Very simple, clear calculations that I think, one should either find a mistake or one should say that, or one should accept them. So that's the first point. The second point, I just wanted to respond briefly also to the point about a closed universe. Bernard, I agree the closed universe is very interesting. In a closed universe, there's an interesting version of holography, which is if you define some gauge fixed observables, you can label them by points. And there the statement is that any open set on the late time slice has information about the whole. So there's no boundary. But the way I framed it actually is that the complement of a bounded region has information about the whole. So if the universe is closed, that's the reason, that's why I phrased it that way. Any open set is a complement of a bounded region.
I'm a bit confused about that because in quantum gravity, there are no regions in a sense, right? Because
I know. So I said, correct. Yeah. So I said, if you look at gauge fixed observables, which are labeled by points, I could explain to you in more detail. Okay. But these are, you're right that those are not gauge invariant observables, but there's a notion which, if you look at gauge fixed observables that are labeled by a point, they're not really localized. Right. And the last point about relational observables, you're right. You can define relational observables. In fact, we recently wrote a paper. The talk I gave today morning was about relational observables. But those are really coarse-grained observables. If you construct them, you can see that they're limited. And they're not good for asking questions about unitarity and black hole evaporation. What they are good for is saying why we see an approximately local world. So if you wanted to ask about inflationary correlators, as we do, that was, in fact, as I was speaking about today morning, you should use relational observables because, their locality is good. But if you want to ask about black hole information, I think you shouldn't. So that I think that, relational observables are good. They're a feature, not a bug. But I don't think they're, you can see also where they break down. Mm-hmm. Okay, so that's what I wanted to say. Please go on, yeah.
Sorry. Thank you all to the panelists for both of the presentations again. They were all marvelous, and for the discussion. I was told that the session would be approximately an hour and a half. So I will unilaterally say that we can go until 4:40, let's say, to make up for the 10 minutes that we started late. And of course, if people need to leave before that, feel free. So the first question from the audience, Larry, you have your hand up. So yes, audience, if you have a question, please raise your electronic hand. Larry?
Yes, I would like to address, can you hear me?
Yes.
Right?
Yeah. Yes, I'd like to address a question to any of the panelists who care to respond. And this is about the possible role of subtle correlations in the Hawking radiation. That is, that the radiation is not exactly thermal. And I want to emphasize this by a simple thought experiment. Suppose I write a message on a piece of paper, burn the piece of paper, and for the sake of this argument, assume there's no information remaining left in the residual carbon atoms. Then I think we all would agree that the message was carried away by subtle correlations in the photons that left the burning paper. So now the question I'd like to pose to any of the panelists who care to comment on this is this analogy at all relevant to the black hole case?
I
will request that actually all three of the panelists reply, but briefly.
I can reply in 1 second. Yes, in my opinion, it's a very good analogy. Yes, of course, the information comes out with the photons in your case, and the question is when it comes out. A black hole shrinks. Does it come out during the evaporation or after the end of the evaporation from a remnant or from some in a time scale longer than the m cube? That's a question, it seems to me. We have reasons to believe that the second answer is the right one. Raju probably disagrees.
Yeah. No. I actually with the first statement, which is that I agree completely. These subtle correlations are important. I think that's a perfect analogy, and that's the reason I, in the talk I gave, I quoted Hawking's point, because often what people say is, look, Hawking computed thermal radiation, and of course we know there are small corrections and they're sufficient to carry information, like in the piece of paper. But that's why Hawking's argument went one step further. He said, look, locality tells you even those small corrections can't happen. So that's why the key point is, can you argue that there is a way in which the information, the region outside has maybe very small, exponentially small information about what's happening inside. And that's why this principle of holography is very important. So I would agree completely that that's a perfect analogy. But in the case of black holes, even to make that analogy work, you have to argue that, locality doesn't work the way it does in ordinary quantum field theories, because then the information outside would have nothing, would have no information about what's going on inside. I don't agree with Carlo that, the information comes out in a remnant. I think we have many calculations in many control systems that show that the information comes out the way it would. And in fact, I would say that the information is outside at all times, first of all. So it doesn't have to come out. You make measurements outside, the information is outside at all times. But, the idea that somehow the information goes in and stays inside, I mean, that's I feel, not justified. And it's based on this QFT and curve space-time argument, which neglects the constraints.
Bernard?
Okay, well, I would say in a formal mathematical sense, because the time evolution is unitary, the information is present in the final state, but it's completely inaccessible because, so to speak, we can't measure the state of the gravitons that our matter is entangled with. So you genuinely have lost information.
Okay, thank you. So next question is from Rakesh Jha. I hope I did not mispronounce that too badly.
Yes, yes, sir. First of all, thank you all the speaker. This is a very insightful talk. So I am struggling problem for many days in context of the Rindler waves. So I am trying to do the Unruh effect kind of thing. So what is my setup? So we have taken just a right Rindler waves and call it as a R1. And we have taken that the vacuum state in R1 as a R1 itself. Here we have didn't taken any Minkowski as a vacuum state. And then we have another Rindler wave, which is the null shifted along R2. And when we are looking from the R2, so we get the selective thermalization, like some modes are thermal and some modes are still in vacuum. But the problem is when we try to define the state in this system, so because there is no any well-defined complement exist in this, so I got the state is pure. So is it consistent with the information paradox, or I am doing something wrong?
Well, since that was strictly speaking not a question about any of the talks, I will leave it up to the discretion of the panelists whether they would like to engage with it or not.
I'm sorry, I didn't fully understand the question. There was something about the right Rindler wedge, and then what came next?
So in right Rindler wedge, so we have another wedge that we that shifted along the null direction, like any of the axis U or V axis. So R1 and R2 along the null direction. So we have shifted. So we just want to see the this thermality with respect to the R2 that is shifted wedge.
So Rakesh, you're asking a question about what sounds like a fairly involved setup that I don't think any of the panelists or most of us are familiar with. And so I don't think this is the best forum to be asking that question. Yeah. So I strongly recommend, and the panelists may dislike me for this, that you email your question to the panelists, and then they can engage with you in what I think will be a more appropriate forum for this.
Okay.
Thank you.
Okay.
And are there more questions from the audience? So we have, according to what my declaration earlier, 6 more minutes.
If there's no question, I can make a small point.
Absolutely, please.
This is a comment to what Bernard says about entropy and the need to find a definition of entropy, and then what he said about being vague, subjective, which raised an important point. So I would react, and I wonder if Bernard would agree with us the following. Entropy is not a thing, an absolute thing that we have sort of mysteriously tried to capture. We can give different definitions, and there are different things which we can call entropy because they overlap in many cases, but they don't overlap in other cases. So there can be different entropies. I don't think we have to look for the real one. We have to give useful definitions first. And some of them have properties, of course. I mean, some of them have the properties of growing in time for statistical reasons in some way and so on. Second point, I don't think there is anything vague or subjective in entropy. I think there are things relative. But to be vague and subjective, vague is different than subjective, and vague and subjective are different than relative.
Mm-hmm.
So entropy is always relative to either a cross-graining or an algebra of observables, or a split of the system in two parts, which give some algebra observable and therefore gives a graining.
Mm-hmm.
So if we have a black hole with a certain area, certain geometry, and a quantum field on this geometry, there is an entropy which is well defined, which is just on a Cauchy surface, a trace over the internal degrees of freedom, and you have the phenomenon over the other. And that might or might not be related to the area. So I don't see this vagueness. I see an interesting fact about which definition of entropy, so which subalgebra which define a close graining, is interesting with respect to the thermodynamical property of the second principle. Would you agree with that?
Not entirely.
Okay, good. So
for example, if you look at Page's papers on where he derives the Page curve, he equates the entropy.
Oh, yes. Sorry for interrupting you. That's what I'm saying. I mean, Page is making a confusion between the thermodynamical entropy and phenomenal entropy. That's what I insisted. Each is well defined. Is confusing the two, which is the source of the problem.
Well,
Page is making reference to the thermodynamic entropy at all. I mean, I think I would say my objection to the argument by Page is that he's assuming a factorization of the Hilbert space between inside and outside. But if you just look at the Page argument in setups where that factorization is kosher, like, you divide this table into two parts, non-gravitational system, that's a theorem, right? That's just using the Haar measure, and you look at the entropy for Haar typical states. Now, I would say that in the case of a black hole, you shouldn't factorize it into outside and inside. That factorization fails because of the constraints and because of holography. So that's why I would say, my objection to Page's argument is I think the Page curve is flat, not that it doesn't go up and go down. I mean, I think actually Page might agree with this, but
Raju,
I mean,
you don't need to think about factorization of the Hilbert space. You just think to say it's a fact. There's a subalgebra observable which are outside.
Yes,
and
but those might be complete.
Those are
complete, then the entropy is zero, right? If you just look at the question is, does the subalgebra of observables outside have a commutant or not? And I would claim it doesn't have a commutant. In a non-gravitational theory, it has a commutant. In the theory of gravity,
so we're now getting down into some serious technical details that I think would be best left taken offline.
Yeah.
Before we go on to the final question from the eminent and well-known researcher CSE/203, I would like to invite Bernard to see whether he has any final response to the questions about entropy that Carlo asked.
Yeah, well, I was going to say, if you look in these papers by Page, for example, he defines he equates the entropy of a black hole, which he takes for granted as a quarter of its area, with a microcanonical ensemble.
Yeah. And
it has to be microcanonical because the black hole has a definite mass, or at least approximately a definite mass. So he equates the entropy with the logarithm of the number of energy levels between m minus epsilon and m plus epsilon, where m is the mass of your black hole. But what's vague is the epsilon. It's simple.
I agree with I agree with you 100%.
Okay, then I actually think that if I'm correct, CSD /203 is done. Don, do you have a final question?
Well, I did have a question, but it's also maybe a bit specific and technical on Suvrat's talk. But if that's not a problem, I'm still happy to ask it.
So yes, please do.
About your statement that you can essentially reconstruct bounded region, or at least that all the information about bounded regions should also be available from its exterior. It feels very Schlieder-like to me, and also the states, the asymptotic states you presented are very specific in that they have very nice analytic properties, such as that they satisfy a Schlieder property. But are you saying that all states in quantum gravity should satisfy this Schlieder-like property, or is it a bit more? Is it more than that, actually?
First of all, I think it's important to distinguish this from Schlieder, because Schlieder holds also in quantum field theory without gravity. In Schlieder, the statement is that the action of the algebra of an open set gives you the, is dense in the full Hilbert space. That's different from what I'm saying here, because Schlieder doesn't rule out the fact that you have a commutant for operators in an open set, right? In ordinary quantum field theory, there's a unitary operator that's localized in one region, another region, and they just commute. So Schlieder is a statement about the Hilbert space, that the action of operators in a bounded region gives you the whole Hilbert space. So this is much stronger than that. This is saying that if you look at operators in the complement of a bounded region, that algebra doesn't have a commutant. So that has nothing to do with Schlieder. Now, the statement about Schlieder, I think it's important to say, Schlieder follows from something called the spectrum condition in quantum field theory. What we need to use in our proof is not Schlieder, but we need to use the positivity of energy. It's actually weaker than the spectrum condition. So what we needed to assume was that the energy as measured at Scribe plus by the ADM Hamiltonian was positive. And that I feel is a reasonable statement in a theory of quantum gravity, that, actually the energy is bounded below. So positive is, you can set the zero in whatever way. So that's an assumption we indeed need to make, that you're looking at states where the ADM Hamiltonian is bounded below. Of course, we can't prove the assumption, but I think that's a reasonable assumption. So we don't need to assume Schlieder, which involves, as I said, a slightly stronger spectrum condition. But we need to assume the positivity of energy. Then we prove not Schlieder, but some version of Schlieder, which we need as an intermediate step. But the final result is much stronger than Schlieder. And the assumption is about positivity of energy. And I think that's reasonable. I mean, okay, we can argue about that, but I think in quantum gravity, it's reasonable to assume, if quantum mechanics makes sense, that the Hamiltonian is bounded below.
Okay.
Thank you very much.
I'm happy.
So we're now well over time, so I would like to draw proceedings to a close. But first, please join me again in thanking the panelists for what I think was a really wonderful set of presentations and discussion. And I also would like to thank again Elena and Paolo and Benito and Don and Elizabeth for not only for organizing this wonderful event, but for the entire SCONE project, which I think is great. So thank you very much, everyone.
Thank you so much, and thank you also to Carlo and Bernard for the discussion.
Thank you, Raju. Thank you, Bernard. Thank you, Erik. Thank you, everybody.
Thank you.
Thanks,
Thank you.
everyone.
Bye.
Yeah. Also from the organizers, of course, thank you very much to whoever's still here. There will be more meetings coming in the next year as
Starting February.
And if you're on our mailing list, you will hear about that. Thank you very much for attending, and hopefully see you next time.
Yeah.
Thank you. Bye.
I just want to say I said something and I realized I was muted. So I just said thank you to Carlo and Suvrat, and I think we've clearly got a lot to discuss, and hope we can be in touch.